In this video, we're going to see a number of optimization problems which are intrinsically non-linear but can be reformulated as linear programming problems. And this will always be due to the presence of piecewise linear convex functions. The first thing we want to do is define what is a piecewise linear convex function. So this is a function of this form. F of x is the maximum for I that ranges from 1 to some number m of a number of affine linear functions, so of the form Ci transpose x plus a constant di. To visualize a piecewise linear convex function, we have an example below. To be able to visualize it, in this example, x has only dimension 1, while in general, of course, x is just an n-dimensional vector. So what do we have in this example? We have exactly 3 affine linear functions. The first one is c1x plus d1, the second is c2x plus d2, and the third is c3x plus d3. So these are the 3 functions inside the max. So we're taking now the max, and so for each point x, the value of the function f of x is given by the highest among the 3 corresponding lines. So for example, for this point here along the x-axis, we have one function gives us this value, one gives us this value, and one gives me this value. And so since we have the max, we're going to choose the largest. If we do this for every x, we are selecting always the affine linear function with the largest value. The most well-known example of a piecewise linear convex function is the absolute value. In fact, the absolute value of x can also be written as the maximum of x and minus x. In this case, as you can see, this is the function minus x, this one is the function x, and the maximum gives us exactly the absolute value. Great, so now let's think about piecewise linear convex functions inside linear programming problems. So let's consider a constraint of this form, a piecewise linear convex function less than or equal to a number h. Of course, this is not a linear function, therefore we can't directly use it in our linear programming problem. So the setting you should be thinking of is that you already have a linear programming problem with a bunch of linear inequalities, and then you have these additional constraints. Let's say you have a solver to solve linear programming problem, and you can't just use the solver with this inequality because it's going to return an error telling you that this is not linear. However, there is an easy way to write this constraint using only linear inequalities. In fact, it is easy to check that the maximum of a number of functions is less than or equal to h if and only if each function is, in fact, less than or equal to h. Therefore, instead of writing this piecewise linear convex function, we can write all the m linear inequalities cix plus di less than or equal to h. Let's see an example. Here we're minimizing a linear function subject to non-negativity constraints on the variables, and then we have this piecewise linear convex constraint. This is not a linear programming problem, but we can transform it into a linear programming problem. So everything we have to do is replace this inequality with two inequalities, x1 plus 2x2 less than or equal to 2, and 2x1 plus x2 less than or equal to 2, which is exactly what we've done here. Formally, we should prove that these two optimization problems are equivalent. We know how to do that, but in this case it's really trivial because we know that the feasible region is exactly the same among the two problems, and this immediately implies that they are equivalent because they have the same objective function. So we just understood how to write in a linear programming problem inequalities of the form piecewise linear convex function less than or equal to h. Now, what if instead you have a similar inequality but with greater than or equal to h? This is a good exercise for you. Think about it. Are you able to write down this inequality in a linear programming problem? So we've discussed how to deal with piecewise linear convex functions among the constraints. What if instead we have piecewise linear convex functions in the objective function? For example, a problem of this form. You're minimizing a piecewise linear convex function subject to a number of linear constraints. Also in this case, we will be able to write down this problem as a linear programming problem, but it will be just a little bit more tricky. So the function that we're minimizing is this piecewise linear convex function, max Cix plus di. Now the whole idea that is needed to make this transformation into a linear programming problem is to realize that this maximum is equal to the smallest number z, which is larger than the max. This is really obvious because what we're saying is that z must be greater than or equal to the max, but we're picking the smallest such z, and this will be the z that satisfies this inequality at equality. So of course we will have z equal to the max, which is exactly what we want. But we have seen an inequality of this form before when we were discussing constraints, and we know how to rewrite with only linear inequality a constraints piecewise linear convex function less than or equal to z. How can we do that? We can replace it with z greater than or equal to ci transpose x plus di for every I that ranges from 1 to n. So we've just understood that our max is exactly the smallest z that satisfies all these constraints. So we replace the max in the objective with z, which is to be minimized, and we add among the constraints all the m linear constraints that we have just introduced. Clearly what you have obtained is a linear programming problem. What you can check is that this linear programming problem is in fact equivalent to the original problem. And I'm gonna leave this as an exercise for you. While working out this exercise, you will also realize that it is really fundamental for this argument to go through that in the original problem we are minimizing this piecewise linear convex function as we are, because if you replace that minimization with a maximization, then things are quite different. Let's see an example. Here we are minimizing our piecewise linear convex function, which is the max of two linear functions subject to a number of linear constraints. So the idea once again is to replace the max with z, and z should be greater than or equal to both the functions in the max. So here they are, z greater than or equal to 2x1 plus 4x2, and z greater than or equal to 2x1 plus x2, while the other constraints remain unchanged. Next, we're going to see optimization problem involving absolute values. Let's have a look at an optimization problem of this form. So we're minimizing the sum of ci absolute values of xi subject to some linear constraints ax greater than or equal to b. And we assume that all the ci's are greater than or equal to 0. Now it can be shown that this is just a special case of what we have just seen, namely that the objective function, the sum of ci absolute value of xi, is in fact a piecewise linear convex function. In order to show this, you would need to write it down as the max of a number of affine linear functions. And once you've done that, then you can write this optimization problem as a linear programming problem as discussed previously. However, this requires some work, and there's a much quicker way to deal with this optimization problem. Essentially, the trick is to apply our previous idea not to the whole objective function, but singularly to all the absolute values. So let's pick one absolute value of xi, and as before, we observe that this is the smallest number zi that is at the same time greater than or equal to xi and minus xi. So then the absolute value of xi can be replaced with the zi in the objective function, provided that we add among the constraints xi less than or equal to zi and minus xi less than or equal to zi. If you do so, you obtain the following linear programming problem. Minimize the sum of ci zi subject to ax greater than or equal to b, which were our original linear constraints, and xi less than or equal to zi and minus xi less than or equal to zi for every I. This is a linear programming problem with variables xi's and zi's. Once again, you should show that the linear programming problem that we have obtained is indeed equivalent to the one we started from. In proving this, you will realize that the assumption that all the ci's are greater than or equal to 0 is fundamental for this equivalency to hold. Let's see an example. Here we're minimizing to absolute value of x1 plus x2. In this problem, as you can see, there is the absolute value only on the variable x1, so we only need to introduce one additional variable z1, because for x2 there's no need to introduce any new variable. So we replace absolute value of x1 with z1 and add among the constraints that x1 is less than or equal to z1 and minus x1 less than or equal to z1. Next, we're going to discuss data fitting, which is one of the most fundamental techniques in data science. There are several different ways of doing data fitting, and we will see that at least a couple of them can be written as linear programming problems. So let's state our data fitting problem. We are given m data points. Each one is of the form ai, bi, where ai is a vector in Rn and bi is just a scalar. We would like to extrapolate from this data a predictive model that is able in the future to predict bi given ai. One way to think about this problem is the following. Let's say that every I is a test patient, and every entry in the vector AI is the result of a test that this patient took. For example, A1 could represent blood pressure, A2 could represent the age of the person, A3 could represent the weight, and so on and so forth. And then BI tells us if this person has a heart disease or no. Then, in the future, whenever a new patient comes in, the idea is that we can test all the A vector for this new patient, and we want to be able to predict this B based on the previous observations done on our M test patients. In this situation, we often use a linear model of this form, B equal to AX, meaning that if a new patient in the future will come in, we measure the vector A, then multiplied by a vector x that we have obtained from all our previous data, and in this way we obtain the predicted B that tells us if this new patient has heart disease or no. Here, x is the parameter vector to be determined using our M test patients. A fundamental quantity is then the residual or prediction error of the parameter vector x. And this measures, for every data point, how well our vector x predicts bi given ai. So this can be written as the distance from ai transpose x to bi, which can be written as the absolute value of bi minus ai transpose x. Clearly, we are searching for an x that minimizes this prediction error. However, remember that we have m different patients, so we have one prediction error for each patient. We essentially want to minimize all these values at the same time, and there really are just several ways to do that which are not equivalent. So one way is to minimize the largest residual. In this way, our problem becomes minimize the maximum residual. And this is exactly a problem of the form that we have just seen. We are minimizing a piecewise linear convex objective function. In fact, this is the maximum of the two M functions, which are bi minus ai transpose x and ai transpose x minus bi, because each absolute value is the maximum of these two functions. So we can immediately write a linear programming formulation for this problem. We replace the piecewise linear convex function with a z, and then add the two m inequalities that say that every affine linear function inside the max is less than or equal to z. And here they are. In this way, you can solve your data fitting problem with a linear programming problem. But remember, the one we have written here is not the only way to interpret our data fitting model. Another possibility is to minimize not the maximum residual, but the sum of all of them. Of course, you obtain a different problem, but you might be interested in this one instead. Also in this case, though, you can solve this problem as a linear programming problem. Once again, we use the same idea. We replace every absolute value with a new variable, ci, and add the constraints that bi minus ai transpose x and its opposite are less than or equal to zi. So we obtain the following equivalent formulation. We minimize the sum of all the zi's from 1 to m, subject to bi minus ai transpose x less than or equal to zi, and minus bi plus ai transpose x less than or equal to zi for every I. You can check that you have obtained indeed an equivalent problem. And clearly the one that we have obtained is indeed a linear programming problem. And this concludes this video on piecewise linear convex functions.